Good morning. My name is Amy Fagan. I'm a graduate student at the University of Notre Dame working with Clive Neal. My current research topic is Apollo 16 impact melts and their petrogenesis. We've actually found something fairly unique about impact melt samples from around the lunar module site. If you talk to anybody with a basic understanding of petrology and you ask them what the rare earth element profile looks like for a plagioclase crystal, they'll tell you it's pretty linear, but you have a nice peak at europium. This occurs because europium is approximately the same size and charge as calcium, so plagioclase will preferentially take it up. We are actually finding that while we do see rare earth element profiles of plagioclase crystals like that at the Apollo 16 site, we actually also have some crystals that have a negative europium anomaly. To our knowledge, this has never been seen before, so fairly unique and a little weird. We've also found that most of these analysis points, with the exception of one, comes from the lunar module site. It does not come from any of the rest of the stations. So something unique is really going on at the lunar module site that we've not necessarily seen before. We're still trying to work that out. But we do have a poster. It's at Delta 23, entitled A Unique Petrogenesis for Impact Melt Samples at the Apollo 16 Lunar Module Site. I'll be at the poster this evening at the poster session. Please come down. I would really love to discuss my research with you. Thank you.
Good morning. My name is Bobby Kohanim. I'm a PhD candidate at MIT in the Aeroastro department working with Professor Jeff Hoffman. My research is specifically on how we can take small vehicles and quickly traverse them across the surface and how we navigate and guide those vehicles. What I'm going to be talking about today is a collaboration that we have with some different departments at MIT, the EAPS department and the Physics and Astronomy department, as well as some folks at Draper Laboratory, where we're developing new ways or new platforms for exploring the surface of the moon. So I'll be talking today about hoppers and penetrators and how they can enable certain science. My talk is at 4:30 in the showroom. Please come, and I hope to discuss more there. Thanks.
Hi everyone, my name is Ryan Clegg. I'm a graduate student at Washington University in St. Louis. I work with Brad Jolliffe. In the past, I worked with Phil Metzger at Kennedy Space Center looking at the blast effects of landing rockets on the moon and the interaction of rocket exhaust with lunar soil. And now at WashU, I've been doing some research with looking at the photometric anomalies around the Apollo landing sites and doing some analysis with that. So we know that particle properties such as composition, compaction, texture, particle size distribution will affect how light is reflected off the lunar surface. And the blast zones around the Apollo landing sites appear as distinct photometric anomalies in LROC images. This is due to the smoothing of the surface during landing and the fine particles being blown away from the lander. So we're using HAPKI functions to try to extract different soil particle properties and determine the behavior of soil during the launch and landing of spacecraft. It also has implications for comparing the data we get with remote sensing data for determining how much soil was blown away. Sorry. And then I'm also doing kind of another side project looking at actual Apollo samples from Apollo 17, high titanium samples, to get the composition of titanium across these samples and compare them with UV and visual remote sensing. And I don't actually have a talk, but you're welcome to come, or a poster, sorry, but you're welcome to come and talk to me. And I also want to put in a plug for Phil Metzger's talk during the Apollo Historic Landing Site meeting tomorrow afternoon about protecting the landing sites. Thank you.
Good morning, my name is Patrick Donahue, and I am also a University of Notre Dame graduate student with Clive Neal. And I guess I like alliteration, so if you don't remember anything else, remember PET, petrology, petrography, petrogenesis, and poster. I have a poster at D22 today, and like I said, I do petrography on Apollo 17 high titanium basalts. Poster is type A basalts, petrography to petrogenesis. We use crystal size distributions, spatial distribution profiles, and combine that with quantitative compositional analyses using laser ablation, ICP-MS, to really pick apart the small scale changes that occur in these rocks, to compare those with the really good whole rock analyses that have already been done. And also Quickuloblastic is my Twitter name. It's probably the laziest form of social media that you can do, but I try to spread the word about lunar petrology to some other geologists that I keep in touch with on that. So thanks.
Good morning, I'm Katie O'Sullivan. I am also a graduate student at Notre Dame with Clive Neal. My poster is entitled New Insights into the Lunar Magma Ocean Crystallization Hypothesis. I'm using two samples, a Pharaohan anorthosite 15415 and a lunar tractolite 76535. And I've been doing some crystal stratigraphy work with these, determining trace elements on these. And my findings indicate that maybe we don't know too much about the lunar crystallization, lunar magma ocean crystallization hypothesis. Maybe some of our fundamental assumptions are not quite right. So please stop by. I'd love to discuss this with you guys. And thank you very much.
We're all happy to be here, especially today, since 42 years ago, July 20th, humans first walked on the moon. I'm Louise Rio Frio. Well, Rio Frio is quite easy to type. You only need 2 fingers to type it. And the first syllable of Rio Frio rhymes with the last, kind of like Einstein. I'm a graduate student at University of Houston, Clear Lake, and since attending the first Lunar Science Forum back in 008, I had the great honor of working with the McKay Group at Johnson Space Center, handling real lunar samples. I was able to open up the largest regolith sample ever released to research, and my poster is about something even more exciting. Evidence from Apollo missions to the moon may show something that's going to turn physics upside down and greatly increase our understanding of how the universe began. The speed of light is slowing down as we speak, and the evidence comes from the reflectors that Neil and Buzz left on. This will greatly increase our understanding, lead to new theories of how everything began, why the universe expands, whether it's ever going to slow its expansion, even how the planets formed. And well, it's poster number A7, like the Corsair, in the front row, and I'll be there during the poster session, lunchtime, and anytime you just want to grab me and ask questions, I'm certainly looking forward to them, and thank you.
Good morning. My name is Mike Zimmerman, and I'm a NASA postdoc at Goddard Space Flight Center, and my advisor is Bill Farrell. My poster, which is poster number B1, focuses on using particle and cell simulations to characterize the plasma environment in permanently shadowed craters. And it's well known that as the solar wind plasma sweeps past the moon, it creates a global wake extending many lunar radii downstream. And by direct analogy, the same process is expected to happen in shadow craters at the poles. And my simulations have provided new insight into the critical role that the plasma surface interaction plays in wake formation, mini wake formation at the poles, and also in modulating the fluxes of charged particles to the surface of the crater. Perhaps my most important conclusions are that the plasma particles do get into the craters. In particular, the protons are accelerated toward the crater floor by a combination of ambipolar plasma expansion and thermal processes, and you can almost imagine a waterfall of protons flowing over the crater wall and impacting the floor not too far downstream. And secondary emission from the surface, or the splash of plasma particles coming back off the surface, plays a role in modulating the wake structure, in particular the electric potential. And this work has implications for understanding the sequestration of volatiles in polar cold traps, understanding dust transport and charging at the poles, and also it's already feeding forward into models of charging and dissipation for exploration infrastructure. And again, my name is Mike Zimmerman. My poster is B1. I'd really like a chance to tell you about what I've been working on, and I'd like to show you some great simulation snapshots of the proton waterfalls at the poles. Thank you.
Hi, I'm not a student any longer, but being new to this community, I can consider myself to be one. My name is Valery Tenishev. I am from University of Michigan. Back in Michigan, we have a long history of developing and applying magnetic hydrodynamic types and Monte Carlo kinetic models of dust and gas to planetary and cometary environments. What I'm doing is trying to adjust our Monte Carlo kinetic model to simulate interaction between solar wind and surface of the moon. It's not surprising that simulation of such kind of problems numerically very demanding. So, for example, for the result that I have presented here on the meeting, we use about like 2 million cells to discretize the gas flow in about 600 million concurrently simulated particles. It's a huge number, but it's an indicator that the model that we use is smart enough to be able to handle large-scale computational resources, and as a result can be applied for real-size problems. At any rate, it's worth to use this result. In the result that I have presented here on the meeting, we have simulated solar wind protons scattered on the surface of the moon. The most interesting feature that we have found is a wave-like structure of scattered protons formed behind the moon. The distinctive feature of the solution is that distribution function of this proton is different from distribution functions of original protons of the solar wind, so it possibly makes them distinctable. Making the model myself, I'm pretty much sure about numerics, but the question is what is the physical content, and that I definitely need help for. So if you have any word of advice or just would like to take a look on the pictures, please see me at my poster. Poster is E15. Thanks.
All right, thank you all. If we could all thank the students again one more time, that'd be fantastic. So we have about